Hello, everybody. We're going to finish module 14 today. I hope everybody is doing well. Remember that you can always join me on Fridays. That's also good just to have some social contact with somebody if you want to talk to other people. But if you have questions about this section, you can join me on Friday in our Zoom meeting room that we have. But there's not a lot of information to cover to finish this module. There's not a lot of information, but you're going to have to do on your own that are left. So I think it's 8 to 10, and then you're going to have review questions and practice problems. So you're going to have plenty of things to do this week. This section is about capacitors. So it's kind of an introduction to capacitors. It's not very elaborate. And not only that, but there are all kinds of capacitors, and we're mostly going to be talking about parallel plate capacitors. What is a capacitor? It's a passive element designed to store energy in its electric field. This energy can then be provided to a circuit at a later time. Okay, what does this mean? A passive element means that it does not generate energy. It generates an electric field. So it generates an electrical potential that can generate potential energy that then can be translated into kinetic energy, which can give energy for particles to move. So that it can do. But it's basically a place where we store charges. Capacitors consist of two conductors. Those are parallel plates for the kind of capacitors we're going to be talking about. We have two parallel plates made out of metal that are separated by an insulator, also called a dielectric, represented by this distance right here. This space is your insulator or dielectric, and it's going to be air. Basically is air. Okay, so you have two plates that are connected by a wire in your electrical circuit, and we're going to be talking about electrical circuits in our next module. And you're creating two different kinds of charges on the different plates, positive charges on one side, negative in the other, and of course you already know that they are attracted to one another, meaning that because they cannot travel through the air, they will be creating this electrical field. Okay, electrical field, electrical potential, potential energy, kinetic energy, then electrons can move in that wire. Okay. I think I explained everything in this picture. So let's move on to the next one. I said to you that this module for this year, the kind of capacitor we're going to be talking about is the parallel plate capacitor. So you have two plates made out of metal divided by an insulator, which is air. The area of the capacitor and the distance between the two plates are important when you want to calculate how much electrical potential potential this can generate. So we're not going to be using it a lot, but know that the area and the distance are important. Okay, well, let's see. To explain this picture, A represents the area of the plates, D represents the distance, Q positive are your positive charges, and Q negative represents your negative charges. And that E right here in the middle is your electrical field. You already know that. The arrows are pointing that way because they come out of the positive and are trying to go into the negative. We have learned all of these. Let's keep looking. Here's another visual representation. This is an electrical circuit. Here you have your battery with a positive and negative plates. You have your arrows because you're creating those plates, positive charges, negative charges. And the insulator or dielectric, which is another name for the insulator, is your air. So once you have this set, you are creating an electrical field. Another thing you need to know that at least for this course, if you have 10, a plate that's charged with 10 coulombs that are positive then the negative plate needs to be charged with negative 10 coulombs. Okay? For this course, if they give you a positive plate that is charged with 10 positive charge coulombs, then you know that the negative plate then is charged with negative 10 coulombs. Okay, now this is explained as well. Another visual representation of the same thing. So capacitors are used in electrical circuits to store charge. So right here, you're storing charge. Here's your negative because it's your negative side, and here's your positive because this is your positive charge in your battery. Capacitors in a circuit will absorb any voltage fluctuation. They're there to protect things that you are hooking to your circuit. So here is a light bulb. Okay, there's a filament right here that has a bulb. If there is too much charge running through this circuit, this filament will burn out. So to prevent that you put a capacitor right there that will absorb the voltage fluctuation. It will store charges. Okay, so far so good. Let's continue. And remember that if this is not making sense, you can read it also in the book, and then on Friday you can come to me and ask me questions. But I think it's not too complicated. Of course, we have a mathematical way to calculate the electrical potential of those capacitors. We have a new formula for you, a new equation. The electrical potential, when we're talking about capacitors, can be calculated by using this equation. Q divided by C of Q. What does that mean? Well, Q is the total amount of positive charge stored in the capacitor. That's why it was important that you knew if they give you the negative, you could find the positive because they are the same, at least for this course. Okay? And then C of Q is the capacitance of the capacitor. That's a mouthful. But what does that mean? What's the capacitance of the capacitor? Well, it's the amount of charge a capacitor can hold at a given voltage. And it depends on the size of the plates. Remember I said the area of those plates was important. And also the separation between the two plates, the distance was also important. We're not going to be using any formula that allows us to calculate that. Our problems are going to give us C of Q, or if they're asking for the C of Q, they're going to give us the rest of this formula, okay? So we're not going to have a new formula to calculate that. That's explained to you on page 472. How do we apply this? Let's look at example 14.5. Let's read it first. That's on page 473. A 2.6 times 10 to the minus 6 farad, and I think I forgot to say that to you. Just a minute. The units for the capacitance of a capacitor is in farad, F, which just means coulombs divided by a volt. Okay, that's all it is, but it has a new name, farad. So now that we have looked at the units, let's go back to our example on page 473. So we have a 2.6 times 10 to the minus 6 farad capacitor. So they give us the capacitance of this capacitor. It's charged up so that there is 2.3 millicoulombs of total charge on its positive plate. Look at these units, we need coulombs, so we're going to have to change that. What is the electric potential of this capacitor? Well, this is just applying the formula. This is all it is. It's just an application of the formula. Let me find my whiteboard. It's not really a whiteboard, it's a blackboard, but I think it's better when it's black and white. Let me go here to my board. So we're trying to apply the formula. Let me get my numbers. So our I wanted to have it in black. Let me go to a black background. Great. And let me get white. Well, why is white not appearing in here? Here you go, white. Okay, so they're asking for the electrical potential of these capacitors. So they're asking for these. They want to know these. And the formula says that that is the amount of our positive charge divided by the capacitance of this capacitor. There you go. That's the formula we need to use. It's an direct application of this formula. We have everything we need. We just need to have the right units. So our electrical potential here, it's going to be the 2.5 times 10 to the minus 3 coulombs. We had to change the millicoulombs into coulombs by dividing by 1,000. And the capacitance was given to us. So that's 2.6 times 10 to the minus 6 farad. Okay? Put everything in your calculator and compare your answer to the book or to the number I'm going to give you. 9.6 times 10 to the 2 volts. Remember that the units for electrical potential are volts. So there you go. I should have put it in yellow if I want to be consistent. So there you go, yellow, okay? Our answer. Now that you have seen these, please do extra practice problem number 8 on your own. That means stop it right here, stop the video, and try to do this problem on your own. And then I'm gonna also do the problem. I'm gonna do the problem, and if you don't get the same answer as what I'm gonna give you, then you can see how I did that, how I solved the problem. But if you get the same answer, just move on in the video. So let me go back here. Let me get a new page. And this problem reads, well, let me give you first the answer. So if you get the same answer, you don't have to do anything else. The answer for number 8 is 1.01, make this point a little bit darker, times 10 to the 8 farad. So if you got this answer, you can move on. If you didn't get this answer, watch to see how this is solved. Number 8 wants to know what's the capacitance of a capacitor that stores 9.09 times 10 to the 8 coulombs of charge at a 9.00 volts of electrical potential. So that's what they are giving us. You have only the one formula that connects all three. So write down the formula first. Okay, that's the original formula. And then you need to decide, what are they asking? They want to know the capacitance. The capacitance is these. They want to know these. That means you're going to have to change, you're going to have to modify this formula to find C of Q, the capacitance. Let's do that. The capacitance is going to be our positive charge divided by our electrical potential. We're going to use this modified version of the formula to find our capacitance. Let's do that. Let's go to another page. And we have everything we need. The positive charge was 9.09 times 10 to the 8 coulombs. And our electrical potential was 9.00 volts. So you have everything you need. Just put it in your calculator to get that 1.01 times 10 to the 8 farad. I'm gonna put it in yellow, but this is the answer. So if you didn't get this, probably you're doing something wrong with your calculator. Let's go back to instructions. So go back here and let's move on to the next slide. I'm going to assign these for you to do at home. I'm going to give you extra time to find anything that you may need for that. Remember to look ahead to see if you need to order anything online, if you don't want to go shopping to Walmart. These are very basic things like balloons and aluminum foil and stuff like that you're going to need for this experiment. But I'm going to give you some time to get all the materials that you need. Now, application of capacitors. That's going to be on page 473. Things to know, really. When a particle travels from the negative plate in a capacitor to the positive plate, it experiences an increase in electrical potential. Okay? Because it was all about, okay, let's continue. If it moves to the opposite way, it experiences a decrease in electrical potential. So let's see, maybe I need to look at this in here, in this picture right here. You have your capacitor, negative plate, positive plate, dielectric or insulator. So there is a space full of air. And there's a voltage, meaning that you have an electrical field that's creating an electrical potential. And this apparatus right here, a voltmeter, can tell you how much electrical potential you have here, okay? But it says, when a particle travels from the negative plate, so we're traveling from here to here, okay? We're going to say that there is an increase in electrical potential. If it's going the other way, from here to here, then there's a decrease in electrical potential. So far, so good. We say that the capacitor was capable of storing energy. It can store charges. And then those charges can be released very rapidly if you needed it to. It can be released. Let's read this right here. The capacitor stores separate charges, which create a potential difference. You already know that, okay? Each of the charges has electrical potential energy due to the position in the electrical field of the capacitor. You already know that as well. We have been working with this concept. Depending on where you place that charge, the distance, okay, will increase or decrease the electrical potential. Remember, we have been doing this. Change in electrical potential equals the electrical potential final minus the electrical potential initial, and that had to do with the position initial and final. So position where you place it inside the capacitor is important. There's nothing new here, really. So let's move on. Let's see. We're not going to be using these formulas mostly. This was just because you can see that everything is connected. Everything we have been doing, okay? Everything we have been doing so far is connected. We use capacitors to accelerate charged particles. That's what we do because you are storing charge. That charge will translate into electrical potential. Electrical potential will change into potential energy. Potential energy translates into kinetic energy, and that's where you have your velocity, which can give you acceleration. Okay, you know this. This is all the same thing we have been talking about, so nothing new here. The greater the charge in electric potential, B, the greater the change in potential energy. Yeah, we know that. The greater the change then in kinetic energy and the greater change in the speed. So this is all the same thing we have been doing, okay? There's nothing new. Don't get scared with all these formulas. Let's move on to the next slide. Let's put all this information together. Here's the good stuff, okay? So, how do we apply all this information, all these concepts that we have been learning all along, all of it together in a problem? Let's read this example 14.6. If a freely moving electron, so we have a negative charge, okay? It has a mass, it has a charge, starts at rest and travels from the negative plate of a 3.1 times 10 to the negative 6 farad. So remember, this is the capacitor to the positive plate. How fast will it be moving? Assume that the capacitor has a 0.55 millicoulomb of stored charge. Please watch out for units, okay? So this has everything. It has everything we have learned. All that information, all in one problem. Let's see how this is solved. Let me get started. I don't know what happened here. New page. So the question is, what are they asking? How fast will it be moving? So velocity. You want to know the velocity. That's our question. Where did velocity come from? Velocity, you can find velocity in your kinetic energy. Kinetic energy is 1/2 the mass of the particle that's moving. So it's going to be our electron right here times the velocity square. That's where it comes from. So we need to modify this formula to find the velocity. You did that before. Square root of our change in kinetic energy multiplied by 2 divided by the mass. Okay, maybe I need to stand this a little bit more. Okay, so this is the formula that would allow us to find our velocity. What are we missing? Okay, once you have the formula, you have to start thinking, okay, what do I have? What am I missing? They give us the mass. Number 2 is just a number. So we're missing this right here. We're missing the kinetic energy. Start thinking, where can I find my kinetic energy? What do I know? Well, I know, and you know it too, okay, that the change in my potential energy, okay, will provide my kinetic energy. And they are oppositely related. So when this decreases, this one increases. When this increases, this one decreases. So this is how you relate one with the other. That would be dandy if we already had the potential energy. We don't have the potential energy, but we know how to find the potential energy. How do we do that? Well, what is our potential energy? Let me put it right here because I have space. Okay, what is our potential energy? A change in potential energy equals the charge that is moving multiplying the change in electrical potential. Okay, so that's the other formula you're going to need to be using. You have everything now. Once you have this, you'll be able to find the kinetic energy. When you have your kinetic energy, you'll be able to find your velocity. That's how you connect everything. So let's try to find what we're missing. We do have the charge that's moving. We have that value, but we don't have the change in electrical potential. We can find it. We know how to find the change in electrical potential in a capacitor because we have another formula that allows us to do that. So let me go. Oosh, I don't want that. Sorry, I want a new page. So I need to find that change in electrical potential within the capacitor. What formula allows me to do that? The formula that allows me to do that is this one. The last formula you have learned. Okay, this will allow me to find the change in electrical potential in that capacitor. Do we have the information we need? Let's see. Did they give us the charge that was positive? Did they give us that? Yep, they did give us that. Assume that the capacitor has a 0.55 millicoulomb of stored charge. That is your Q right there. The problem was that they give us the information in millicoulombs, and we're going to have to translate that into coulombs by multiplying by 10 to the negative 3, or you can divide it by 1,000. You already know how to do that. So let's put that information in. 0.55 times 10 to the minus 3 coulombs. Okay, these are coulombs now. Divided by the capacitance of this capacitor. Did they give us the capacitance? Yes, they did. F, anything that has an F for their units, that's your capacitance, is farad. So 3.1 times 10 to the minus 6 farad. It's an F. Okay, put this in your calculator. Okay, put it in your calculator, and you should be getting a value of 1.8 times 10 to the 2 volts. Okay. We just found the change in electrical potential. If you remember, we needed that to be able to calculate our potential energy. So now that we have it, let's calculate that potential energy. The change in potential energy, we said that was our charge multiplying our change in electrical potential. So let's put that information in. Equals. The movable charge here is your electron, and they give us the charge for that. Negative 1.6 times 10 to the minus 19. Remember that we are keeping the magnitude. We're not doing absolute values. We're keeping the positives and negatives for the charges now. And we just calculated the change in electrical potential. We said it was 1.8 times 10 to the 2 volts. Put everything in your calculator and you should be getting a change in potential energy of negative 2.9 times 10 to the 17 joules. Okay? So what do you know? You know that the kinetic energy, the change in kinetic energy is the same magnitude, but you change the sign. So now we know that our change in kinetic energy, because if one increases, the other one decreases, is going to be 2.9 times 10 to the 17 joules. Great. Now we know our kinetic energy. That means we can place it inside this formula right here to find velocity. Let's do that. Let's do that. So our velocity now equals 2 times change in kinetic energy divided by the mass of the particle that is moving. So we have everything we need because we just calculated the kinetic energy. 2 multiplying the 2.9 times 10 to the 17 joules. I'm going to extend these. Divided by the mass of this particle that is moving, and that's the electron, and that was given to us. So 9.1 times 10 to the minus 31 kilograms, and kilograms is what we needed. So put everything in your calculator. Just put it in. And if you do the math, you should be getting 8.0 times 10 to the 6 meters per second. This is our answer. They were asking for the velocity. So 8.0 times 10 to the 6 meters per second. Pretty fast, isn't it? Very good. I forgot to tell you before that the potential energy, the change in electrical potential. Sometimes it's a mouthful to say that. But let me see, where did I calculate this? It was this one? No, it was this one. This one right here remained positive. Okay. Be careful because I said to you that if it was traveling from the negative to the positive, then it remains positive. It stays positive because it travels from the negative to the positive plate. But if it was traveling the other way, okay, you would have to change this value right here. And I think you're going to see an example of this pretty soon. So now that you have done this example with me, let's try 9 and 10, okay? Let's try 9 and 10 to see how this works. Let me get my solutions module so I can just write your answer, and if you get the answer correctly, you can move on. We don't have to, well, you don't have to do this. For number 9, so the value for number 9, you should be getting a value of, let me see, positive 1.8. I don't know why I proposed it, but okay, times 10 to the 7 meters per second. So if you got this answer, you can move on to number 10. If you did not get this answer, please watch the video to see how this was solved. And let me get my numbers right here. Remember that the solutions manual has a different way of approaching the problem. So you can look at the solutions manual, or you can look at the video to see how it's solved. He usually thinks it backwards, at least in my opinion. He puts the information in a kind of a backwards way. So the problem reads like this. An electron, and they give us the mass, they give us the charge, is placed at the edge of the negative plate of 9.0 times 10 to the negative 6 farad. So they give us the capacitance of the capacitor. If the capacitor holds 8.5 millicoulombs of charge, remember that this is the charge, the positive charge, the big Q. How fast will the electron be moving when it reaches the positive of the capacitor? The positive of the capacitor? Did I read it right? The positive plate of the capacitor. Okay. So what's going on here? What are they asking? This is very similar to the previous problem. They're asking for the velocity. Velocity is our question. Okay. Remember that velocity comes from your kinetic energy. So you can find it right there. 1/2 the mass of the moving particle plus d squared. So rearrange these and you'll find your velocity. Velocity equals the square root of 2 times change in the kinetic energy divided by the mass. This is the formula that will allow us to calculate our velocity. So what are we missing? Well, we do have the mass. Number 2 is not changing, so we're missing these. We're missing our kinetic energy. Let's find it. Where do we find our kinetic energy? Our kinetic energy is found if we can find our potential energy. When one increases, the other one decreases. That's what the law of conservation of energy says. Energy is not created or destroyed, it's just being transformed from one to the other. So we don't have this. We don't have the potential energy, but we have a way to find that. We know that potential energy, change in potential energy, equals our charge that is movable times our change in electrical potential. Well, we're still missing something. We're missing these. We do have the movable charge, that's your electron, but we don't have the change in electrical potential. We can find it. How? Because this is a capacitor, okay, you need to use the formula for the capacitor. And that formula says that to find the change in electrical potential, you need to have the charge of the capacitor divided by the capacitance. And they give us both. Okay. So the only tricky part here is to check the units. They give me millicoulombs for this. So I need to change my millicoulombs into coulombs by dividing it by 1,000 or multiplying by 10 to the minus 3. So 0.0085. I divided by 1,000. But you could have just multiplied by 10 to the minus 3, which is the same. It is coulombs. Divided by what? The capacitance was given to you. So just find the number. 9.0 times 10 to the minus 6 farad. Okay. Put this in your calculator. Put it all in your calculator, and you should be finding a change in electrical potential of 940 volts for that capacitor. Now that we have this, we can put it in the other formula. But let's think about this. Yeah. Let's read it for a second. It's moving from the negative plate. Okay, so that should be fine. It's traveling from the negative plate. to the positive plate. So we can leave it like it is. Okay. So that's another step. You need to decide. It's going to stay positive. Yeah, just the way it is because it's traveling from, you put it in green, it's traveling from the negative to the positive plate. Okay. So you needed to make that connection. We keep it positive the way it is. Now, let me go back to white here. I can place this in this formula to find my potential energy. So do I have my charge that is, I'm going to get another page. I'm sorry, but it was kind of crowded. So I'm going to write it again. Do I have the value of the charge that is moving? Yeah, I do. It's my electron that is moving. So that was given to me. Let me find it in my problem. That is minus 1.9. Sorry. Let me do this again. 9.9 is wrong. Is negative 1.6 times 10 to the negative 19 coulombs. Okay. That's my charge that is moving as my negative charge is an electron. And we just found the electrical potential. So find that information in your page. And let me find it here. Just calculated it, but I don't want to have to go back. 940. 940 was my volts. Put everything in your calculator. Once you put everything in your calculator, you should find a change in potential energy of negative 1.5 times 10 to the minus 16 joules. This will allow me to calculate my kinetic energy because I know that they are connected, same magnitude, opposite signs. So positive 1.5 times 10 to the negative 16 joules. Great, I can go back to my formulas, remember, and I can place it, I didn't go far enough. Maybe this one, yeah. I have my kinetic energy, I can place it in the velocity and find my velocity. So, new page. My velocity equals the square root of 2 times my change in kinetic energy divided by the mass of the particle that is moving. So I have every single thing I need. 2 times 1.5 times 10 to the negative 16 joules divided by the mass 9.1 times 10 to the minus 31 kilograms. And we wanted kilograms. If they had given us grams, we would need to change that into grams. But we didn't need to do that. So put everything in your calculator. And your value here is 1.8 times 10 to the 7 meters per second. That's our answer. The answer that I gave you at the beginning. So if you're not getting that number when you put everything in the calculator, you're doing something wrong with your calculator. And try again. Use your parentheses. You can also break it down. You can do the top, then do the bottom, and then finally do the square root. Okay, let's look now at number 10. Number 10. Okay, so number 10, according to, it's easier to find it in the solutions manual instead of looking at my paper. The answer for number 10 that you should be getting is 5.0 times 10 to the 5 coulombs. So if you found this, you're done, okay? But if you didn't, you can watch the video to see how it was solved. Let me read it. Let me find my instructions. It says, a proton with a mass and a charge, so they give you the mass and charge of the proton, moves from the positive plate, watch it, positive plate, to the negative plate. So we learned something about this. They give us the capacitance of the capacitor, so 4.2 times 10 to the minus 3 farad. if it starts from rest and reaches a speed of 1.5 times 10 to the 8 meters per second, how much charge is stored in the capacitor? So what are they asking for? They're asking for the charge that is stored in the capacitor. Where do we find that? The formula we have, okay, says that the change, this is change, okay, or the voltage, okay, is going to be our charge divided by our capacitance for that capacitor. So they're asking for this right here. They're asking for, well, maybe I should just color it. Maybe not. Doesn't look too good. Anyway, they're asking for this charge right here. So that means we need to modify our formula. Let's modify it. This like this, looks like this. Our charge is going to be the change in our electrical potential, or electrical potential if they give it to us, multiplying our capacitance. Okay, what do we have? What do we need? They give us the capacitance, okay, that's given to us, but they did not give us this right here. That means we need to find that. How do we find that? Well, they give us information for speed, okay, but if you remember, the formula that allows us to calculate the change in electrical potential looks like this. Sorry, I should not modify it from the beginning. Sorry. Let me look at this. Pen. Okay. Remember things. Change in potential energy equals the movable charge times change in electrical potential. It's a mouthful. So, if I want to modify that, so I can find my electrical potential, new electrical potential. I should write it down again. Okay. You have it in front of you, but I don't. Okay. So that right here, I want these to go on the other side, so I can have my electrical potential by itself. This is the modified formula. Do this using algebra. So I need to think now. Okay, I do have the value of my charge that is moving. They give that to us for a proton that is moving, but I'm missing the change in potential energy. But I have a formula that allows me to calculate that. My change in potential energy is the opposite of what happens to my kinetic energy. Okay, great. Do I have a way to calculate my kinetic energy? Yes, I do. My kinetic energy is 1/2 the mass of the particle that is moving times the velocity of that particle that is moving. And guess what? They give us everything we needed. We have the mass and we have the velocity. So let's calculate that kinetic energy. Okay, kinetic energy equals 1/2 the mass times the velocity squared. Okay, let's put everything in. What was the mass? The mass of my proton in kilograms, which is perfect because they already gave it to me, in kilograms is 1.7 times 10 to the minus 27 kilograms. Okay, and I'm multiplying this by the velocity, which also was given to me, was 1.5 times 10 to the 8 meters per second. I'm not going to put it there because I don't have a lot of space, but is squared. So put everything in your calculator. And the velocity, once you do the velocity, you should get a velocity, let me find it in my paper, of 1.9. Not velocity, what am I talking about? The kinetic energy, 1.9 times 10 to the 11 joules. Okay, so now I have kinetic energy. But remember, that's not what I need. I need the potential energy. We know they are connected, but one increases, the other one decreases. So I know that my change in potential energy will have the same magnitude, but opposite sign. So negative 1.9 times 10 to the minus 11 joules. I'm not done yet because I'm going backwards. This was just so I could calculate the change in electrical potential. So let's continue. Remember that the change in electrical potential was the change in potential energy divided by the charge that was movable in coulombs. I have everything I need now. I just calculated this. That was negative 1.9 times 10 to the 11 joules divided by the charge. The charge was given to me in coulombs, so I don't have to do anything. I just need to place it in there. It's a positive charge. It was a proton. So just copy the information they give you in the problem. Put it all in your calculator, and you should find a change in electric potential of minus 1.2 times 10 to the 8 volts. Okay. Now, usually we report the potential difference as positive. Remember what we talked about. That let me find a different color. We kept the sign right here if it was going from the negative to the positive side. But if you read the problem, it doesn't say this is what's going on. Okay. Let me erase these and let me read the problem to you. The problem to you, you have to be careful when you read. It says it moves from the positive plate to the negative plate. So it says it's moving from the positive to the negative plate. Okay. So when that happens, you are going to have to change the sign. Okay. You also, if you don't want to think about it this way, you can think about the fact that the different potential in a capacitor is usually positive, is given as a positive number. So you can directly change it or just think it's because it's traveling from the positive to the negative. I have to change the sign. Whatever makes sense to you, okay? So this is what we're going to be using. We're going to use the positive version of our change in potential, electrical potential. Okay. Okay, here we go. We're on the last stretch of this problem. Now we are ready. Now we're ready to find the charge of this capacitor. If you remember, that was the change in potential, electrical potential, times the capacitance of our capacitor. So we just calculated this. We had to change the sign because it was going from the positive to the negative. Okay? And that is, I'm going to put it in parentheses, 1.2 times 10 to the 8 volts. Multiplying the capacitance, and that was given to us. Okay, that's given to us. So just put the number in, 4.2 times 10 to the minus, is it 8? Let me see. Cannot even understand my own handwriting. Minus 3. I think it is minus 3. Okay? So put all the numbers in. And once you have that, that's where you get the 5.0 times 10 to the 5 coulombs. And that was the answer we mentioned at the beginning. Okay? Lots of steps, a lot of things to think about. It's putting all the information we learned with the information we learned last week with all the new formulas and the old formulas. So it's everything together in this one. Everything together. Okay. To finish the module on page 476, the book explains to you how a TV works, really, how a television makes its picture. I think you just have to follow what it says in there. There's not a lot to that could be difficult. There's no math involved here. There's nothing to apply to a problem in here. But read this part of the module. I'm not going to go over it because I just will be repeating what it says in pages 476 and 477, and you don't have any problems to do with these. But it's all summarized in this picture if you want to use the picture to understand what's going on in there. Okay. Well, you all keep safe. If you have any problems with the problems, if you have any problems with practice problems, with on your own, anything of that sort, please meet me in Zoom so we can go over the problems together. Please keep safe, and I'll keep posting.